Okay, now, use a calculator. Or you can use Excel if you enter this function in. I think these are the correct numbers. That 0.33 might actually be a 0.34. So I'll leave it to you to check that out. Your trapezoid here then extends from z equals 0.6 to z equals 1.3. Its altitudes are graph altitudes. They're actually bases. But its graph altitudes are 0.33 and 0.17. So we can easily calculate any characteristic of the trapezoid we like. It's only a single trapezoid, so there's not going to be any accumulated area, and there's not going to be any rate of slope change. And the slope really is not important, so we're not going to bother to calculate it, but I'll just remind you we easily could. The average graph altitude, which would be this, would be the mean of these two, which would be like 0.26. So the average graph altitude is 0.26. The width is 1.3 minus 6, which equals 0.7. So area is 0.26. And this is just approximately, I mean, this is the, and we're actually approximating the area of the trapezoid as well, but 0.26 times 0.7, well, that's actually 0.182 if I multiply correctly. Okay, so I had an estimate of 23%. Well, looks like I drew my normal curve a little high. I kind of thought my 60% was a little high. So things came out a little higher than they should have, and maybe my eyeball on these areas and so forth wasn't as good as it could have been. So that's about 18%. Okay, then I estimated 23%. That wasn't a great estimate, as I just said. Well, that means that if I took a bunch of SIPs with this mean and standard deviation, about 18% of them would come out between 17.2 and 18.6, assuming that the SIPs are normally distributed, which they might well be. When we analyzed the 10 SIPs, it was very plausible that there was a normal distribution. Probably ought to repeat the experiment with gulps. There'd be more grams in a gulp, so we would have smaller percent uncertainties between two readings, okay, because this thing reads only to the nearest gram. We don't really know where we are in between the grams. Okay, well, that's an illustration of normal curve, the meaning of an area under the normal curve, formula for the normal curve, calculating an area under the normal curve, estimating an area, eyeballing it, and then how we might reason out the number of standard deviations. Any particular number on the x-axis is from the mean, and that would be the z-axis. So z-values how many standard deviations from the mean. And actually z-value would be a displacement. So if you were on this side, your z-values are negative. And x-values on this side, of course, would give you negative z-values. And you already know that from the way you've drawn the curve.